Okay, welcome back, everybody. Welcome to this last session on optimization and data-driven techniques. Again, we have three very interesting talks in this session. And the first speaker is Miguel Nóbrega from the University of Minho in Portugal. And he's going to tell us how he optimizes profile extrusion dies.
Okay. Thank you, Andre, for the kind introduction. Thank you, everyone, for being here. So the work I'll present today is a joint work for University of Minho, as Andre mentioned, and Soprefa is a company that works on the design of profile extrusion dies in the production of actual profiles, and in the University of Genoa, the host of OpenFOAM Workshop, specifically Joel Guerrero, that took care of the optimization itself. I hope I will not disappoint you. I will not really talk with the details of optimization. Is more on the part of the design and the achievements we managed to get with this project. This is the outline of the presentation. So I'll start with introduction, explain you the problem we had to solve, then describe the code that was developed to do it, the integration of the code, because there were different parts of the code and we had to integrate them, some case studies, and the impact of the solution we reached. It's too late for that, obviously, but yesterday we had a session where we described in detail the codes that were developed, and these codes are public and will be are available in a GitHub. For later, you can see this presentation if you are curious about the details of the actual implementation. So another important detail is that this work was funded in the framework of an European project for TCMO4, and the purpose was to join academia and industry to illustrate the advantage of resorting to HPC in order to design or to solve real problems. There were persons on the side of the industry, of Soprefa. There were persons inside related to optimization, as I mentioned, Joel Guerrero, and also the group from the University of First of all, the problem. When we are trying to design, to manufacture a plastic profile, one of the main limitations we have, one of the main difficulties we have to solve is the flow balance. Usually, most of the profiles comprise different thicknesses, and since they comprise different thicknesses, naturally the flow will concentrate on the thicker sections. And it's in order to proper design a profile extrusion die, you need to have a balanced flow distribution, or try to have a balanced flow distribution, and to do it, we need to design the channel. This might be obvious for simple flow channels, but when we are dealing with complex geometries, this is quite difficult and requires a lot of trial and errors. Typically, in industry, they don't resort to any software. They do it by experimental trial and error basis. And the main problem is that it's resource consuming, and it requires a long time for tool development. We're talking about 2 to 3 months to reach to the final solution, and it can reach up to 10 trials when they are dealing with a realistic profile, or even more. Or in some cases, and it happens often also, it's not possible to reach the desired solution. So the purpose here was to try to combine numerical modeling and running in HPC with this need for the design in order to figure out if you can reach a good solution. In order to do it, as you might advance immediately, we had to integrate a simulation code, a CAD software, because we want to have automatic system, and then optimize. So for simulation code, obviously, we used OpenFOAM. For the CAD software, we used OnShape. OnShape was our first choice because there was previous experience of the team with OnShape, and it runs in the cloud. So it's quite flexible and allows to have an easy solution to implement. But the company, in order to use the real cases they have, they were not allowed to use OnShape. They didn't have a license of OnShape, but they had a license of Fusion 360. And at the end, it was the software we used more because of that restriction from the company. The framework is flexible. So at the end, as long as the generation of geometries can be automated, we can use any software. And for the optimizer, we use Dakota based on the experience that was also previous experience from Wolf Dynamics that was involved in the project. So, in order to be able to model non-isothermal flows with proper viscosity models for polymers, we performed the implementation of a new solver or a different solver from the ones available in OpenFOAM. So that follows the simple method, and we coupled it with the energy equation and a model to be able to compute the viscosity based on the temperature and the shear rate for the material. And it's an incompressible flow. This is what happens in reality for these kind of problems. And this is it. It was not it was a simple implementation. And in order to be able to account for the performance, to calculate the performance of a specific geometry, we need to somehow evaluate the quality of the flow balance. And in order to do it, we did is we divided the cross section, the outlet cross section of the profile into different sections. We call it ES, the elemental sections, and IS, the intersection sections between different elemental sections. And for each geometry, in each of these subsections, we calculate the flow rate, and this objective function, you have to trust me, but this objective function tends to 0 for a perfectly balanced flow, and it has a large magnitude when the flow is not properly balanced. But this allows us to somehow calculate the quality of the flow balance. And for that, we implemented a function object to be able to compute it. Give you a quick example of how the system works. This is one complex geometry that was tried also inside the project. There's a huge number of elemental sections and intersection sections. And this is the geometry, the real geometry. And okay, the code is able to compute the flow field for pressure, the outlet velocity, or the full velocity. But what is relevant here is the outlet velocity and the temperature distribution of the system with the specific functions. Also, in the code development, we after solving the initial problems, we figure out that we didn't have to wait for residuals conversions to get the solution. If we observe the objective function, and you can see from this line over here, it tends to a steady state value earlier than the residuals, and that allows us to stop the calculation of the trial earlier than we would do if we wait for residuals conversions. Okay. The next step is the code integration, and the code integration to give you an idea for OnShape what we did. So we have the HPC cluster where the files for the geometries for the parameters of the geometry are generated by Dakota. Then that information is used to update Python scripts. Those Python scripts are run and go to the cloud, update the geometry, generate an STL, and that STL is used to make the simulation, read results, write results that are fed again to Dakota. and that is used to update the geometry. Using Fusion 360 was a bit more complex because Fusion 360 runs in Windows, and we are not able to run it in Linux as the cluster. And the solution we came up with was to synchronize both through a cloud system where the file and the data is stored. So the process starts as we did for the previous OnShape, generating geometries. Then the geometries or the parameters are sent to the cloud. There are files that are used to trigger the processes, that are generated to trigger the processes, and those files, when they are running, there is a Python script also running in Fusion that is waiting for the file to appear, and when the file appears, it starts generating geometries, create the STLs. Then the STLs are sent to the cloud, and they are sent to the cluster, and then Fusion is waiting for a new request of a new geometry, and the process in the cloud continues, the cluster continues until the solution is the optimized solution is reached. We tried, or in the framework of the team, tried different approaches, and the last one that was used is this machine learning library, XGBoost, with the method. This is the information or at least the conclusion we reached for this specific problem. And Joel is not here. I might not be able to give you details if you want to understand why we choose this one. But we tried different approaches based on his experience, and that was the selected one. Before moving to the actual problems, we did also a scalability studies in order to figure out which should be the best configuration to run the problems. And in order to do it, we tested for different case studies, and I'll give you more details about those case studies right after. Depending on the type of configuration, number of nodes, and the number of tasks per node we use, we managed to run 500 problems in the time frame of 1 day, and that was the kind of configuration we used to set up the different problems we tested. And what you can see here are the profiles that were really tested in this framework. This one I already showed you before, a large number of sections and the parameters that were used to optimize. Another one that has less tests, but it's a symmetric profile. That's why the representation is like this one. There is another symmetric profile, this one, that was also tested, and all of them had different materials. And this was the last one. So in the framework of the project, we optimized for different profiles. Some data about the solutions we got. So, okay, different materials, as I mentioned, ABS, PC, HDPE, and PVC. This was the improvement we got from the initial trial to the last trial in terms of the objective function. So there were obviously a few improvements. Improvements in terms of the velocity distribution that was already also achieved. Okay, we ran all the problems in 512 cores. These are the number of geometry trials that were tested in the framework of this time, during this time frame. And this was a major achievement for the project, because in all of the cases, in 1 day, it was possible to optimize the geometry, trying with the number of tests that would be impossible to do if we don't have this automated process running. For curiosity, I also provide the actual costs of having these runs in the cluster. So this is, and I'll show you in the next slide, the actual costs for over design. This doesn't have any meaning on the cost. So the message should be, okay, it's quite safe to use these approaches, and the cost is more than acceptable. Okay, this was not supposed to, but just to show you that two of the problems we test them experimentally. This one, the clip and the easy light, in the framework of the project. So the tools were created and I was just passing by. Sorry, I forgot to because in my computer the noise was shut down. But anyway, so in these two tests, this one went quite well. In two trials, the process was running. In this one, we had a problem that we didn't figure out. It was the profile is symmetric, but the outcome of the tool of the profile, the initial trial, was not symmetric. They managed to solve this to have this profile running as they requested in 7 trials. But we still didn't figure out why, with a symmetric tool, with a symmetric temperature control, everything symmetric, the profile was not symmetric. But even though, based on this, the possible conclusions is that, okay, before the company, the average number of trials was, say, 7.5, between 5 and 10. And assuming that this one was a real one, this one was, this one was a real trial, the 7 trials, that we believe we can do much better. This is something that should not happen in a symmetric geometry. But let's assume we have 4.5 trials in average. These are the costs before and after. The final cost would be of designing the tool is around 18,000 euros, and there is a reduction of 4.2 thousand euros that are mainly related to the development and to the reduction of the number of trials. And this one, okay, that means that before the company had to, everything was subcontracted. Right now they can design their own tools, and this is the cost of the HPC calculation. That is already a reduction in terms of trials, and they have more control of the process. They don't have to share the information with external entities. And so we're talking about a reduction of 40% on the number of trials. That means same level of reduction in the time to market, and a reduction of 20% on the cost of the tool development. So to finalize, for the company, as I mentioned, reduction in terms of time to market, raw materials, the amount of the cost of the actual developments, and they can be more independent. Regarding the other technical achievements, okay, we managed by making use of the objective function, reduce the calculation time by 50% to the half. The optimized solution was able to be achieved in the framework of 1 day, and there is an optimized approach to design, and we're able to tackle this issue, to combine different operative systems to solve the problem. To finalize, if you like to have more fun with OpenFOAM, don't forget we have the wiki and the OpenFOAM journal to publish your activities. And this year, beginning of November, there will be, especially for the Iberian community, an event in Emirates. Thank you. It depends on the profile. In many cases, were the width. In some cases, where was the length as well of the tool. Now, we didn't try to do that. The temperature control in a system like this is quite sensitive, so we try to keep it as uniform as possible. But it's another degree of freedom that can be applied as well, and the code is able to do that. Is in practice is done. It's done for fine tuning. They do that for fine tuning to adjust the tool to be able to run last trials, but that was not used here. But it's a possibility to adjust as well, and we could do it here. But it's for that you need to model the process, even the metallic tool, and we're not doing it here to control. So, no, sorry. What I was saying is that you need to use conjugated transfer to model the temperature distribution in the metallic tool and in the cross section, and it's possible. There was a presentation today where we show that as well, but it requires more calculation time, and we managed to develop the tools. Currently, they are running, but it was not on time for this project. In some cases, it generated tools that usually what we do is the design and parameterization, then we impose limits to the parameters. Okay. In some cases, it generates geometries that were not valid, but it's possible to check in the solution if it converges or not converges, then remove that solution from the system. That happened in some cases. Sorry? Wire, I believe wire EDM, it's mostly what they use, but they also use EDM. It depends on the tools we want to. The company that does the machining, they have all the processes, it's not Sopref, it's not the actual company that is subcontracted. That's why I mentioned the cost doesn't change, the cost of the tool development, the 9,000. Yes. Yeah. In some cases it's possible, but okay. Yeah, there are a lot of degrees of freedom for improvement of this. Thank you.
All right, the next speaker is Markus Towara from Aachen University, and he's going to talk about some hacks that he does with PETSC in order to enable automated differentiation in OpenFOAM.
Okay, thank you. So I was really hoping to be using your presenter, but then I'm just going to stand here. Thank you. That's much more convenient. Okay. Yeah, so I'm Markus Towara. I'm a postdoc at Aachen University. That's a shared position. I also have another job at the numerical algorithms group in Oxford. But today the OpenFOAM stuff is purely academic. And what I'm going to show you here is a lot of work in progress. So I won't be showing much results, but I will be showing you what I did. And first, I want to reintroduce our AD solutions within OpenFOAM. Okay, doesn't actually work. Oh yeah, got it. Okay, so we've been developing on fork of OpenFOAM for a number of years now. I started that way back in 2013, I think. We have forward and reverse mode of AD in there, with also higher orders. So for second derivatives, if they really need it, turns out nobody really wants it because it's really expensive. And also vector modes. I'll be talking about that in a second. And what's the advantage of doing AD over something like finite differences? Well, it gives you very accurate derivatives, assuming that your primal actually behaves well at a comparatively cheap cost. Just as a motivation, I always show this picture, which is kind of derived from Carsten Notmar's work with OpenFOAM for topology optimization, where we have some kind of geometry. We introduce some cells we want to penalize, effectively take it out of the flow by actually adding some term alpha times u into the momentum equations. And in order to do that, of course, you need to know what actually is a decent value for alpha. And that's where gradients come in. And if you want gradients, you have to have some kind of differentiation technique in there. So what you always have to do is you have to define a cost function. So in this example, it's the power loss, which is only related to the pressure loss within like a ducted channel. And then you want to actually calculate a gradient. So this has one output, so it's a gradient with respect to a bunch of parameters alpha. So this could be millions. And then if you have such a gradient, then you can just do some classical optimization thing. We usually just do a really dumb steepest descent and go into the direction of the descent direction to hopefully make the cost function better. And then you do that iteratively until it's converged. And also you have to constrain the parameters in order to make it physically meaningful, so that in this example, we just don't introduce a fan into this, which actually pushes the flow along. So we want to be able to penalize it, but we don't want to give it a boost, so to speak. So we introduce a clamp on these parameters. Okay. So in the work we are doing, usually the number of outputs are really small, so either scalar or a handful of outputs. So Professor Martins already covered this in the keynote yesterday very well. The inputs, however, could either be like millions if you look at the individual mesh level, or it could still be a few hundred to thousands if you do like a spline representation or something, spline representation or something like this. And the beauty of the adjoint method now is that we construct some magic black box which can do differentiation. And by calling this black box m times, where m is the number of outputs, we can get a whole gradient. This is another picture, which in a different form also the Professor Martins showed yesterday, where we show what's the different approaches for this adjoint. So there's a continuous adjoint, which is in OpenFOAM.com since a few years, which is work started by Professor Genoa, which has the approach, okay, we physically derive the adjoint equations, then discretize them and solve them more or less independently from the primal solutions. The primal feeds in there, but the discretization is different. Advantage is, okay, it's fast. If you have some physical knowledge, also it's physically interpretable to look at the adjoint fields themselves. And then on the other side, there's like the computer scientist approach to do automatic differentiation, which we do in our fork, and also what DA-FOAM does by Professor Martins' group, which is a discretize first and then differentiate on this discretization approach. Advantage is pretty flexible, it's automatic, and the derivatives you get are consistent with the implementation. So as long as the implementation does what you actually do, then you hope that you get a decent result. The major disadvantage is that it's very memory sensitive. You need a lot of memory, which especially in this day and age is a bit of a headache, because everybody is going to GPU now, everybody is going to HPC clusters, and the amount of memory per node you are getting is kind of shrinking. But there are ways to tackle this. And generally, it's a bit slower than the continuous approach. Okay, then let's again quickly reiterate what the models of AD are. Again, think about it as a magic black box. So we don't want to discuss here how we come up with these models, but what they allow you to do is in forward mode or tangent mode to calculate a product between some arbitrary chosen vector from the input space dimension with your Jacobian. So if you then need a full Jacobian, you have to do that n times. So it's basically like finite differences, or it's also like the complex step method we saw already yesterday. And now the other part is the reverse mode AD, adjoint AD. Machine learning folks would call it backprop, where you get also a multiplication of the Jacobian, but with a vector of the output space dimension. So you can get the full Jacobian at cost m times cost f, which is great. And then the ideal scenario, of course, is that you actually are not interested in the Jacobian. You just need to get a Jacobian vector product, which, for example, if you're doing a CG or something, is what you're doing. But for us, until now, that has not been an option, so we need to differentiate the whole thing. Okay, if you want to, you can combine these models to get higher order derivatives, second, third, whatever. In engineering applications, I've not seen much use for higher than second order. But for example, people from financial services, they have crazy models which have fourth, fifth order, whatever. And another thing we already heard yesterday, if you have sparsity in your Jacobians and you know what the sparsity pattern is, then you can do a coloring of these, compress it down, and you can further reduce these factors, potentially down to a constant. So now our offering for this AD-fied OpenFOAM is that you can't really see this, but this is a dependency graph between all the OpenFOAM core libraries. So you see it's quite interweaved. So our approach was, okay, just do AD on everything. So we have working discrete adjoint on all libraries within source without any major sheets, as far as I still remember. And then for the solvers, we selectively just treated a few, but most of the important ones still compile. But obviously, if you don't tell it to, they don't do anything meaningful. So stuff like block mesh, SnappyX mesh, pre-post-processing, whatever still works. But we didn't like touch every esoteric solver and fix it. Currently, we don't have any good interaction with the existing OpenFOAM optimization capabilities because they came in pretty late after my PhD was finished. And yeah, now I don't have as much time as I had before to work on this stuff. So we are kind of still using our own implementations. So brief computer science thing, how you actually pull this off is, okay, OpenFOAM has a central type def. I'm not sure if they still use a type def, I think so. Whereas I said, okay, my double scalar is always supposed to be a double. And then they are pretty good. There are a few issues, but pretty good to actually then use this type instead of using double offload. And what we do is we replace this type with our own type, which lives in this namespace AD, which is of our own AD tool, which we ship, of course, with our fork. Also here, I changed it to the more C++ modern style of using. And then you hit compile, and in theory, you have a working discrete adjoint. In practice, not so much. There are some small adjustments you always have to do. And if you have like, I don't know, what are we at now, 2 million lines of code in OpenFOAM, this adds up. So there are like, I don't know, 50 to 100 files you have to touch manually to get this working. So we've been doing that over the years. Every 6 months, I have to pull in the changes and see what happens. And once you did that, you have the running discrete adjoint. So what does this now actually mean if we run it? Just running it makes it slower by about a factor of 5 to 20 doing a first order adjoint compared with just running with doubles. All floating point variables are replaced with our custom AD type. because there is no really easy way to not do this in OpenFOAM. With adjoint AD, we have to create a graph representation, or we call that a tape, of all the code you're running forward, and then you run backward through it. So that's where the memory overhead comes from. And what we also do is that we differentiate through the linear solvers, which obviously you don't really want to do because you actually know what the derivatives are. They are written here. Oh, I forgot the citation. That's in a paper by Mike Giles. So what this tells you here in MATLAB notation is that if you know that X is the solution of a linear equation system A with right-hand side B, then the adjoints of B can be computed by solving another linear equation system A transposed with an adjoint vector X bar, which we get from our AD tool. And then if we have this solution, this is a vector, we can form an outer product between our primal solution X and this adjoint solution we just calculated and get a adjoint matrix A, which still is sparse in our case. We also implemented parallelism in there, which we do with adjoint MPI, called AMPI. And now soon we're going to come to PETSC. If we do this approach here with the linear solvers, we differentiate them symbolically, then our AD tool does not actually run through them. But remember, we still have changed all the floating point types. And we don't really like that, because even if we turn off the tape, the execution of the solvers will be slower by around a factor of 2. So we could gain a factor of 2 if we could just instantiate our solvers with doubles instead of AD types. Unfortunately, it's not that easy. One solution I explored was using this single precision, double precision mode, which in general means do everything in double precision except the solvers in float. I want to hijack that, do everything in my AD type, and do the linear equation solvers in double precision. I tried it, it didn't work. To be totally honest, I forgot why. I think there was a part which was in the single precision notation, but was still somehow part of an active calculation. So cutting that out was a little bit complex. Or my other option I came up with, just use PETSC, because the way PETSC is hooked into OpenFOAM currently. So just to reiterate, PETSC is a PDE library mainly developed by University of Argonne, or no, the Argonne National Labs. It can do a whole lot. The module which exists for OpenFOAM, as far as I know, only does linear solvers. You can run it on CPU or GPU, but it has a different matrix format. OpenFOAM kind of stores its sparse matrices in coordinate style, so you store the IJ index, which we call owner neighbor, and the value, but PETSC does a compressed row storage format. So it has to be converted anyway. And for that, there's this PETSC wrapped vector thing inside the module, which both converts vectors and matrices. And we hook into that. And we do a conversion there from our active AD type back to double. And then, of course, once the solution is calculated, we have to somehow hook this data back in. And nicely enough, this thing here also has a destructor, which is destructed when the PETSC solver instance is destructed as well. So we can use that to go back. So a little bit of code. I don't know if you can really see this. These 4 lines here are highlighted in cyan. I can barely see it in these 2 lines as well. So that's the code change. Everything else was already there before. So only thing is what we have to do is we have to kind of store as a pointer to the old memory location, because all that the PETSC repo does, it does a const cast, removes the const. What we are doing is, as soon as we see that this is actually not just a double, it's an active type, is that we copy the whole buffer, make it passive data, copy in all the stuff from the active data, and then do all the other stuff PETSC usually does, or the wrapper does. If somehow we get in just regular non-adjoint data, so just doubles, we do what we already did before, so this code is unchanged. Okay, so this will allow us to go from OpenFOAM with AD into PETSC with doubles. And then once PETSC is done, all we have to do is we have to delete the other buffer we created. And then before we copy back the data, so there's an optimization, which I don't show here. Of course, if the data is const, then we know the data actually hasn't changed. So then we also don't have to copy it back. Then all we have to do is to do the cleanup here. And so the only thing a little bit unfamiliar about this is like the notation, which comes from our AD interface. So you can get the always the value and derivatives components. Here we are only interested in the value components. Okay, that's all there is to it. If you've never seen it, this is how PETSC FE solution file would look like. So for all of these, I define these for all of these fields. And then during the execution of the program, a PETSC solver of this type, so here it's a BCG solver, is executed. And then, because I told you already, if you need to form the adjoints, you need to solve another linear system. Also during the reverse run, another one of these will be created. So we replaced one linear solver call with two, but that's something we always have to do. That has nothing to do with PETSC. And now the work in progress part. I tried this, but not very exhaustively. So I don't want to show any numbers here, which are misleading. Overall, performance is competitive with what we already have, but it's not significantly faster. But I don't see why it shouldn't be if we find the right cases, because the copy overhead is actually not as bad as one would think. It's a few milliseconds at most for easily sized problems. And the actual meat, which is happening inside the linear solvers, is bigger. So I just need to find an optimal setting or maybe another application for PETSC. So currently I'm doing basically simple form. To summarize, okay, we have a AD-enabled version of OpenFOAM, which you can use to differentiate anything with respect to anything, in theory, as long as it's differentiable. And there are certain kinds of optimizations you can do. One of them is to take out the AD data types for linear solvers. And the way we choose here is to use PETSC. So I'm looking forward to investigate that further in the future. If you want to try this out, it's open source. If you use it, please drop us a line. I think currently we don't have a public facing link, but it's on a public GitLab repo. You just won't be able to find it. But I think I will just add a link soon. Yeah, with that, I'm done. Hopefully I'm in time, and I'm happy to answer any questions. Yeah. To be honest, I don't know. I don't remember. So it's not my code. That's from the PETSC for form. So I hope they're doing something reasonable. It's possible that this is just a wrapper class for matrix, which inside has a reference to the matrix. Yeah, I just said it that it's not as bad as expected. So as I remember it, it was maybe like 1% or something of the actual runtime of these solvers. And so this copying here is something we reintroduce, but the conversion of the OpenFOAM to the PETSC matrix structure, which I suspect is the more expensive operation, is happening anyway. So if there's a major overhead, it's not all our fault, at least. Oh, no, absolutely not. So it's a factor, maybe. Like, of course, it becomes more expensive, but it's depends on your depends on caching things, and if of course then if your linear solver has complexity n cubed, then the factor should go down, I would assume. Yeah.
All right, the last speaker in this session is Runze Mao from Peking University. And he's going to talk about deep learning assisted heterogeneous computation of reactive flows using deepflame.
Okay, thank you for the introduction. Hello, everyone. I'm Runze Mao from Peking University, and it's my honor to introduce our recent work about deep learning assisted heterogeneous computation of reactive flow using deepflame, together with Yinghui Wang from Shanghai Sense-Time Intelligence Technology and Jiayang Xu, Yanzhang Zhichen from Peking University and AI for Science Institute, Beijing. Okay. This is my outline. First, I will introduce the background and the motivation, and then I will show how to port deepflame to GPU, and then I will show the performance, and finally I will show the conclusion and our future work. Okay, first of all, I want to introduce the AI for science method in our group in simulating reactive flow. Okay, in left, I have listed flowchart in simulating reactive flow. This is redesigned from the pinball form in OpenFOAM. Okay, first we need to, in the pinball iteration, first we need to solve the mass conservation and momentum equation. Then we solve the chemical source, and then is species and energy, and next we update temperature and some coefficients, and finally we solve pressure equations and update density. Okay, we can see the different part have different colors. For the red part, it is a PDE solving procedure, and the yellow part is a stiff ODE system solving procedure, and the orange part is some explicit computation. Okay, and the most time-consuming part is solving this large stiff ODE system, right? Even for the most simple fields, hydrogen, okay, hydrogen. This system contains 13 equations and is highly stiff. Okay, and the computational cost takes up to more than 80%. Okay, to focus on this hot point, our partner team, which led by Professor Tianhan Zhang and Zhiqin Zhuan Xu, it produced a method called DIFFERENTIATION, which can use neural network to solve ODE system. Okay, and this is this article for more detailed information. Okay, and now we do not need to solve this large ODE system, but we only need to train and do inference this neural networks. Okay. But how to use this AI for science method in simulating reactive flow? So we developed a open source platform named deepflame. deepflame is the first large-scale open source platform that couples AI frameworks for simulating reactive flow. The deepflame version 0.1 was open sourced in GitHub on June 15, 2022, and has been updated to version 1.2 recently. Okay, this is a main feature of deepflame. It is constructed based on OpenFOAM, Towara, and LabTorch, which is C++ version of PyTorch, have a good support on AI frameworks. Okay, and this is our GitHub link, and you can find more information there. Okay. Okay. So first, I want to introduce how we do an inference in deepflame, and in this figure, we show that actually we use 3 neural networks based on the ignition stage. Okay, the ignition stage is determined by ourselves based on temperature and Q dot, which is actually the heat release rate. And if a cell has a temperature like in here and the Q dot in here and found in this position, we determine it is in post-ignition stage and UN1. And also if it is here, UN2, yeah. Okay, now let's back to the algorithm, how we do inference. Actually, the inference on GPU is implemented by LabTorch, the C++ version of PyTorch. Okay, the things we need to do is to prepare data for this. Okay, and now we assume a complicated condition. If we have multi GPU card and multi CPU cores, and the CPU cores, the number of CPU cores is more than GPU cards. And now we must face a situation that we must do more than one MPI rank, more than 1 MPI ranks, and more than 1 processes need to do inference on 1 GPU. Okay, so we introduce a master worker structure to handle this situation. Okay, at the first, the workers, these 3 ranks send the problems to master, and master classifies the problems like this, and convert data structure from fields in OpenFOAM to torch tensor, and do memory copy between CPU and GPU. Okay, now at the same time, the workers also need to do things. It will solve the left problems with CVOD. Okay, what's the left problems is cells with temperature lower than 700 Kelvin here, and now it can solve very quickly. Okay, we don't need to do inference anymore. Okay, we will show the performance now. This is a toy code. This is a toy case. Is a 3D telegreen vortex. It consists of 2 million cells, and this is the CPU information. And in this case, if we use CVOD to solve the chemical source, and we found it takes up to 83% of our workload. Okay, and now if we use inference and use GPU to do inference, okay, now is only 4%, and the hot points becomes a PD solver at this point. Okay, now let's go to the next hot point. So we need to get a closer look to this new hot point PT solver. It mainly consists of 2 parts. The first is construct the FA matrix, and this is a relative code in OpenFOAM, is FVM, DDT, FM, DIV, and so on, these things. And the other part is solving the sparse linear system. It is solve. The code is just a solve. Okay, and in our general thinking, and this solving procedure is master the main central, and it is also an important problem in HPC community, CFD community, and also applied mathematics community. And so there has many third parties help us to accelerate this solving procedure. And for example, cuBLAS, cuSolver, and MJAX, which is provided by NVIDIA, and Hyper, Vienna, CL, and PS Plus, which provided by HPC and CFD. And also, Professor Chuang introduced MJAX wrapper, which is also makes MJAX variable in OpenFOAM. And follow this, we also use MJAX to solve our linear sparse linear system. However, let's pay attention to this figure. Actually, the time consumed in assembly matrix is also large. It is comparable and even larger than the time spent in solving this linear system. However, there is currently no solution for accelerating sparse matrix assembly, despite their often dominant role. So this is our motivation. And now we will briefly introduce the metric assembly in OpenFOAM. Actually, if we want to solve a equation, it usually need 4 steps. And the first is initialization, and then assembling this, and solving this, and correcting boundary condition. And the assembling procedure is mainly two things: is to construct the coefficient matrix A and the source term vector B. Okay, and this figure shows the relationship between the matrix A and the mesh, and the rank of the matrix A is equal to the number of the cells. Okay, and then the off dialog entry represents phase. For example, if we say this entry, this represents the phase that between cell 2 and cell 1. This and this. Okay. And in OpenFOAM, this sparse matrix is stored and accessed by LDU matrix and LDU address classes. The LDU here means lower, diagonal, and upper. And the LDU matrix store this matrix into three array. And the dialog array it stores this, and the upper array and the lower array. Okay, and the LDU address helps us to access the off dialog entries. Okay, for example, the lower address it represents the column number of the lower elements and the row number of the upper elements. Okay. Actually, porting matrix assembling procedure on GPU has many challenges. For example, on the one hand, the structure of OpenFOAM is highly encapsulated, and it has rich features, including interpolation, format, boundary conditions, correction, and many other things. And on the other hand, the architecture of GPU is also difficult. The GPU architecture and the CUDA programming actually requires a lot of efforts to fully use the parallel nature of GPU. Yeah. So the first issue we need to address is the data structure. First, I want to claim that the LDU matrix cannot be parallelized on GPU due to the red conflicts between phase. Okay, now here is a demo. Here is a demo about the phase loop. If we want to loop phase and try to integrate phase values on cell, okay. If we can say if we want to do thread parallel of this loop, we will find the red conflicts. For example, if we use this matrix, the thread 0 want to write to cell 0, and the thread 1 want to write to 0, 0. So this is a red conflict. So to address this, we need to focus on the per phase field, which includes internal fields of surface mesh, boundary fields of surface mesh, and boundary fields of volume mesh. And we need to change this LDO matrix to CSR matrix. And now the phase loop can be easily to convert to cell loop. And now the red conflicts will no more exist. Okay, the second issue is boundary condition. As we just mentioned, the boundary field is also a per phase field that have red conflicts. And in addition, there are plenty types of boundary conditions in OpenFOAM, and it expands the application scope, but it also increases the complexity of CPU implementation. Okay, and in OpenFOAM, the boundary fields are stored via patch, and so we combine them and reorganize the boundary data according to the boundary cell. And now each CUDA thread can handle one boundary cell. Okay, and with this method, we resolve the red conflicts of a parallel boundary process on GPU. And in addition, we introduce an array which contains the boundary patch type. Include zero, gradient, and fixed value, and many other types. And this helps us to design an interface to integrating different boundary types. Okay. And this is the third thing we do is to do data reuse. we introduced the data registry, and we found it does matter. It does matter on the performance of metric assembly. Okay, for the mesh information and some static informations, we reuse this since initialization. And for the matrix A and vector B, we reuse this inside the equation. And between equations, we reuse intermediate variables, and between iterations, we reuse unknowns per se, which in the four equations is rho, u, y, and ha. Okay, and this method significantly reduces the number of CUDA memory copy cores. And this is our current progress. We have implemented these discretization schemes, and we have finished these data types and data structures, and we have implemented these equations so far, including rho equations, u equations, y equations, and e equations. And this is the result. And these two figures shows the performance of the four ported equations. And we can see in this larger case, about 2 million cells, the matrix assembly gains a speed up of about 18 times. And for the smaller case, we still get a speed up of 13 times. And this figure also shows the overall speed up. And even we currently have not ported the P equation and correct thermal to GPU, but we still get overall speed up close to 3 times. Okay, and this is a summary. With AI and GPU, we solve the chemical source gains 100 times speed up, and moving the bottleneck of deepflame to PD solver, and then we for the PD solver we move the linear system. Use NVIDIA MGX library, and we port the sparse matrix assembly to GPU. And finally, the early results achieve a 10 times speed up of rho, u, y, e equations. Okay. And in future work, we will port the rest operations, including P equations and thermal corrections to GPU, and do further optimizations. And then we will do the multi-GPU parallelizations for PD operations and improve the functionality, and it encapsulates the code for easy use by OpenFOAM community. Okay, that's all. Thank you. Thank you. Okay. Okay. Basically, this red conflicts, I think, is become the loop is based on phase. You see, if we change the loop to cell, now each thread still with a cell. Now we will no more meet the red conflicts. And so if we transpose the LDO matrix to CSR, and each row contains the data of one cell, and we just want to and each thread just one focus row. Okay, and now we will no more meet the red conflict, but it needs some data transfer, but it is not demand. It is very fast. Okay. Yeah. Here the relative sim. Okay, if we see this code, the sim cells, the sim phase here. If phase 0 wants to write to cell 0, yeah. The phase 1 want to write to cell 0. If we do parallel on thread, they write to cell 0 at the same time. So this is also very complex. Okay. Oh, it's no problem. Oh, hello. Sam. Oh, the 100 speed up is this. Pardon? Oh, it's V100. A CPU is also one course, but we haven't achieved parallel. Yeah. In future, okay. No, it's just the last one. So we do it from row equation, U equation, Y equation, E equation, and we haven't finished it. It's not. Expensive. Yes, the P equation is not the most demanding. Is not very special. In reacting flow, in the simulation of reacting flow, the most special, I think the most special is Y equation because it has to solve many equations, and actually it gets most speed up, you can say, and the P equation is not the most time consuming equation. Your question is limited on GPU. Okay. It's a good question because we currently we have not do any optimization about the usage of memory. But for 2 million cells, it will cost about 10 GB on GPU. But I think we will do many things to make it cost lower, cost smaller, management. Okay, so. Sorry, I don't get your problems very clearly. Yeah. Okay. You mean if I use a neural network to calculate chemical source, and it will cost more transport equations? Is this your question? Okay, we will talk later. Okay.